In section 3.4, we're going to look at our most important derivative rule, and that is the chain rule. So we're going to identify the chain rule and then use it to apply the chain rule to find different derivatives. So first, let's start with a motivating example. The temperature H, given in degrees Fahrenheit in a hot air balloon, is a function of altitude y, given in miles. The altitude changes with time t in hours. So there's two kind of functions going on. First function is if we have different altitudes, this is going to change the temperature of the balloon. And altitude changes with time t. So as time is going forward, the balloon is rising up in the air. And we want to find something about bringing these two functions together in some kind of capacity. So the question we're going to ask is, what is the rate of change of the temperature with respect to time? We know something about the rate of change of the temperature with respect to y, with respect to miles, but not with respect to time. So we are given that the temperature is changing at a rate of 16 degrees Fahrenheit per mile. That is the rate of change of temperature with respect to y. And we want to find it with respect to t. So this is the rate of change of temperature with respect to y. We're also given that the balloon is climbing at a rate of 2 miles per hour. This is the rate of change of the altitude with respect to time. And you can kind of see this with the units. 16 degrees Fahrenheit per mile, that's temperature over altitude. Miles per hour is altitude over time. And we have both of these derivatives that is somehow going to give us our final answer here. And this is a motivating example because we can kind of reason out what the answer should be without the need for something called the chain rule. And then we'll see kind of how it's related. So if we know that we are increasing 16 degrees every mile, and we increase 2 miles every hour, how many degrees are we changing per hour? So the change in temperature per hour will be 16 degrees Fahrenheit over each mile, and then times 2 miles per hour. And you can cross out the miles here, and you're left with 32 degrees Fahrenheit per hour. So what's going on here is the change in the temperature with respect to time is equal to the change in the temperature with respect to the altitude times the change in the altitude with respect to time. And this is going to be our chain rule. So note that algebraically this kind of works because we have these dy's cancel out. We're left with dH dt, and we'll see that on the next page. So the point of this example is that we should be able to kind of reason out what's happening without the use of some kind of special chain rule. This is to motivate where we're kind of getting this weird chain rule from. So now let's introduce it formally. The chain rule is used when we have the composition of two functions. That is, we have one function inside of another function. The chain rule says that if y is equal to f of u, we have to introduce a third variable here, or a second variable here, and u is equal to g of x, and that's just another way of writing y equals f of g of x, right? It's like we're replacing u with g of x. So if we have function composition, then we're going to say the derivative of y with respect to x is dy du times du dx. And that's what we kind of did on the previous page. And the reason this is called the chain rule is because if we keep on going in this format, we actually get a chain of these derivatives, one after another, multiplied together. This is nice to write down, but it's kind of harder in practice to use. Note that we also have this du kind of thing sort of cancel out, and then algebraically it kind of looks like dy dx. We are instead going to use the second kind of form of the chain rule. It's the same rule, but a different way of thinking about it. If you have the derivative of f of g of x, the answer is going to be f prime of g of x times g prime of x. So note that this first thing is the derivative of the outside function, and the second one is the derivative of the inside function. And that's what we're doing here. We have the derivative of the outside, f, and the derivative of the inside. The weird thing is that we have g of x in here, but that's just saying that we're going to leave this kind of inside function alone. So here is how I like to think about the chain rule, these steps for computing the chain rule. Number one, and this is regardless what you have to do, you have to somehow identify what are the inside and the outside functions in function composition. And after a few applications of the chain rule, you'll find this is actually the hardest part of the chain rule, is correctly identifying those functions. Once we've done that, we have three things we're going to do. We're going to take the derivative of the outside function, that is f prime. We're going to leave the inside function alone. That is saying that we are going to do g of x inside of f prime. And then we're going to multiply by the derivative of the inside function. So we're going to take the derivative of the outside, leave the inside function alone, multiply by the derivative of the inside, f prime of g times g prime. Note this is function composition, f prime of g, not multiplication. So let's see an example of this at work. The derivative of x squared plus 1 to the 50th power. Step 1, we need to identify the inside and outside function, identify the function composition at play here. So here the inside function is x squared plus 1, and x squared plus 1 is inside of something to the 50th power. Or we can write that as maybe u to the 50th power, or we can write that as x to the 50th power if we want. There's no correct way to maybe do that. It's just kind of thinking what is that outside function, something to the 50th power. The something is the x squared plus 1. All right, step 2, we are going to take the derivative of the outside function. And in this case, that derivative is going to be 50 something to the 49th power, or you can think about it as 50 u to the 49th, or you can think about it as 50 x to the 49th. And I don't care which one you use. I wouldn't recommend writing all three of them. Just write which one works for you. Next step, we are going to leave the inside function alone. So this is kind of where we're combining this idea. We're either going to replace this empty space with the inside function, x squared plus 1, or we're going to replace the substitution u with x squared plus 1, or we're going to replace this x with x squared plus 1. And this is kind of the the positives and negatives of each of these sort of things. I would say the nice thing about writing 50 parentheses to the 49th, it's very clear that there's an empty space that I need to plug into. The downside of that is that it's awkward to write nothing to the 50th power, and it's kind of weird to think about the derivative there. The nice thing about writing 50u to the 49th is that it's clear that u is different than x, right? Something we need to substitute in for. That's kind of nice thing about u is equal to x squared plus 1. But it's a little bit awkward, it's a little bit more difficult because we have to introduce a brand new variable into the equation. And lastly, the nice thing about doing x to the 50th or 50x to the 49th is it's very easy to think about the derivative of that function, but it's a little bit awkward to think about plugging in x squared plus 1 for x. Whichever way you want to think about it works. It doesn't matter to me. Either way, we need to have x squared plus 1 be left inside of that derivative. Finally, we have step 4, and that is we are going to multiply by the derivative of the inside function. So I'm going to write this as 50 x squared plus 1 to the 49th power, and then I'm just going to write times the derivative of x squared plus 1. We don't need to do it all at one step. This is going to give us 50 x squared plus 1 to the 49th power times that derivative, which is 2x. And that is our derivative there. It's important that we don't forget to multiply by the derivative of the inside. That's the step that most students forget, though the hardest step is, again, probably this first step, correctly identifying the function composition. In the next video, we'll go over a bunch of practice problems using the chain rule.